Okay, so today we're talking about limiting and excess reactants. And the idea here is that when you do a reaction and you have more than one reactant, so essentially anything other than decomposition, there's going to be one that runs out. You're never going to be able to stop at exactly the right amount of each ingredient because they're so small. You'd have to have the exact number of atoms and molecules of each reactant that you need, and that's just not going to happen. So one always runs out, and that's called the limiting reactant, or LR. The other is the excess reactant. The important thing here is the limiting reactant always determines how much product you're going to make, because it's the one that runs out. You can't make any more product once one of the ingredients has run out. Once one of the ingredients has run out, the reaction stops. So for example, when you did the little mini lab with the steel wool in class, you had iron, which was the steel wool, reacting with oxygen from the air. Well, of course, you're not going to run out of oxygen in the air. So the iron in the steel wool was going to be your limiting reactant, and that's the one that we used to determine how much theoretical yield of iron 3 oxide you would make, how much iron 3 oxide you should make. So if I have an example of a problem where we need to know which one is limiting and which one is excess, because let's say we can't see it. You know, it's common sense that the oxygen didn't run out when you burned the steel wool because there wouldn't have been any oxygen left in the room, right? And that's just not going to happen. But it's not always so easy to figure out which one was the limiting because you're not doing the reaction, you're not seeing something run out. So an example of a problem just sort of on paper here, if you had, let me keep backing it up here, if you had 200 grams of silver nitrate available to you to react with 200 grams of sodium phosphate, which one would run out first? Well, you have 200 grams of each, the same amount of each, but one of them you're going to run out of first. So the first thing we have to do is come up with a balanced equation. So if I've got silver nitrate, AgNO3, and this is double replacement, so we could go ahead and say aqueous, but I've got sodium phosphate, so it's going to be Na3PO4. And so double replacement, they're just going to trade places, and we're going to get NaNO3, sodium nitrate, which is going to be aqueous. That's my aqueous product, and then we're going to get silver phosphate. So Ag3PO4 is going to be my insoluble solid precipitate. Now to balance, you're going to end up with, let's go ahead and balance my silvers. Balance my nitrates now because I've created 3 nitrates on the left, and that also balances my sodiums. So I should be good with just those 2 3s. All right, so how do I figure out which one is going to run out first? I have 200 grams of each. So I'm going to label that 200 grams of this, 200 grams of the other one too. So one of those is going to be more than I need, one's going to be less than I need. And so what I do, one method for doing this is essentially to take one of those 2 amounts. So I usually just start with the first one listed, 200 grams of silver nitrate. And I'm going to use that number and convert it to grams of the other substance. And what I'm doing when I do that calculation is I'm determining how many grams of sodium phosphate I need. I know I have 200 grams. So I'm going to put the word have next to sodium phosphate, the 200 grams. I can also put it next to the other one because I have those amounts available of both of them. So once I know how much sodium phosphate I need to fully react with 200 grams of silver nitrate, I should be able to determine whether I'm going to have too much or not enough sodium phosphate. So it's just a gram to gram conversion. So let's go ahead and do that. So starting with 200 grams of silver nitrate I'm going to go all the way to grams of sodium phosphate. So I'm going to first go from grams of silver nitrate to moles of silver nitrate. So 1 mole of silver nitrate is 169.88 grams from the periodic table. Okay, and then from grams, I'm going to go to moles. I'm sorry, from moles of silver nitrate, pardon me, I already went to moles. From moles of silver nitrate, I'm going to go to moles of my other substance. In this case, that other substance that I said I'm interested in figuring out how much will I need of it, that other substance is sodium phosphate. And this ratio, going by the coefficients, is just going to be 1/3. And then the last step to get to grams is, of course, I want to cancel moles of sodium phosphate, so that's going to go on the bottom. Grams is going to go on the top. And again, I'm going to go to the periodic table. Should come up with about 163.94. Okay, and so we're going to figure out how much sodium phosphate we need. And if we do the math here, we end up with the number 64.3 grams of sodium phosphate. And I'm going to even write needed right there, because that's going to remind me that this is how much sodium phosphate I need to react with 200 grams of silver nitrate. Okay, so if I have 200 grams of sodium phosphate and I want to use up 200 grams of silver nitrate, I only need 64.3 grams of sodium phosphate. What that means is I have excess sodium phosphate, meaning that my limiting reactant, and I'm going to label it very clearly right up here in my balanced equation or above it, my limiting reactant is the silver nitrate, because I have way more sodium phosphate. 200 grams is way more than I need. And sometimes you can even be asked a question, how much excess is left over? How much unreacted excess reactant will be in the beaker when we're done? So if we were to answer that question, all we would have to do is subtract. So I have 200 grams minus what I need. So that's going to be 64.3 grams. And that's going to be left over, or excess. So that's going to be what, 135.7, I believe. Yes, my calculator verifies. It is 135.7 grams left over. Okay, so once we know which one was our limiting, then we can answer another question that's very important, and that is, how many grams of silver phosphate would you expect to produce? And silver phosphate is way over here in my equation. That's my solid precipitate product. So that's one that we haven't, we were only concerned with reactants earlier. Now we're going to talk about, okay, how much product would we make? And so to do this, you would choose to start with your 200 grams of silver nitrate, because 200 grams of silver nitrate is going to run out. That's what's going to be gone, and when it's gone, the reaction is going to stop. That's very important. If I base my calculation on 200 grams of my sodium phosphate, that wouldn't make sense because the sodium phosphate is not all used up. So we have to always base our prediction of how much product will be made has got to be based on our limiting reactant. And so our limiting reactant is 200 grams of silver nitrate. So I'm going to go from 200 grams of AgNO3 and try to predict how much silver phosphate is going to form. So if I go back up to my balanced equation, there is silver phosphate on the right. Let's go ahead and see if you can, just go ahead and pause, see if you can figure out how much silver phosphate you should make. Do the calculation right now. Okay, so there you can see my work. I went from 200 grams of my limiting reactant, AgNO3, converted that to moles. Then I went to moles of the product that the question was asking me for, silver phosphate. And then using the periodic table from moles of silver phosphate to grams of silver phosphate has a big, big molar mass because it's got 3 silvers in it, 418.58. And so you should have gotten about 164 grams of silver phosphate as your answer. So this would be how much silver phosphate I calculate that I should make if I do everything perfectly, reacting my 200 grams of silver nitrate, because 200 grams of silver nitrate is my limiting reactant. The name for this thing that we just calculated, as you should have learned in the steel wool lab, is your theoretical yield. It's called your theoretical yield because it's how much you should make. If we went and did this in the lab, we may get a little bit less. We may get 150 something, or even 130, 140 something, depending on if we make any mistakes or lose any reactants or products along the way. Okay, so let's talk about a different method to accomplish the same result. So I'm going to show you, this is a second way of doing this type of a problem, but it gives you the same result, and I don't care which method you use. Okay? So first we have to come up with a reaction. So it says we've got iron formed by reacting aluminum with iron 3 oxide. So Al plus iron 3 oxide is Fe2O3. So that's going to give us aluminum oxide, single replacement, and it's going to give us iron. So this is what we're looking for right here. Grams of, I'll put question mark, grams of, well, that's a terrible question mark. Grams of iron is what I'm looking for. Okay? All right. So we are given 113 grams of aluminum. That's one thing we know. And we're given 279 grams of iron 3 oxide. Now, I could solve this problem the same way that I solved the last problem. Starting with one reactant, like 113 grams of aluminum, let's see how many grams of iron 3 oxide I need. And that'll tell me which one is limiting, and then I use the limiting to find my grams of iron. You can do it that way. That's fine. That's the way I usually do it. But I do want to show you another method. It takes the same number of steps, but it's just a little bit different. All we're going to do this time is we're going to separately calculate from grams of aluminum to grams of iron, and then grams of iron 3 oxide to grams of iron. Now we're going to get two different numbers. Then we just have to decide which one is the true theoretical yield. All right, so what I want you to do right now is go ahead and do that. Find your grams of aluminum. Take your grams of aluminum, convert it to grams of iron, and then we're going to do the same thing for the iron 3 oxide. But oops, I almost forgot to balance. Don't forget to do that. We're going to need to put just, looks like 2's in front of aluminum and iron. So don't forget that step. Now go ahead and convert your aluminum to iron and your iron 3 oxide to iron. So I get two different answers, And the smaller one has to be my true theoretical yield because it was based on my limiting reactant.